Hey guys, in this video we're going to learn about the force that two current-carrying wires exert on each other. Our story begins with a single wire, which is carrying a current up the page, and the dots and X's, of course, are indicating the directions of the magnetic field on either side of that wire. Now, if you're not sure on where the dots and X's came from, then you should be using your second right-hand rule. Remember, in that one, your thumb would be the current going up the page here, and your fingers would indicate off to the left that the field would be going out of the page, as the dots indicate, and to the right of the wire, the field would be going into the page, as the X's indicate. Now, we are going to use both right-hand rules in this video. We used the second right-hand rule, as we've been calling it, for determining the direction of the magnetic field. Okay, now the next step is we're going to put another wire near this one. Let's suppose that this second wire is whatever to the right of the first one, and it's carrying a current also up the page, and we'll call this current I2 because it doesn't necessarily have to be the same amount of current. Okay, so we've got two currents now going up the page. Well, if you recall, we learned previously that a current-carrying wire experiences a magnetic force. And you can determine the direction of the force on it using the first right-hand rule. Okay, fine, but wire number 2 is in a magnetic field. The magnetic field that was produced by wire number 1. And since it's carrying a current, it should be experiencing some amount of force. Now, if we want to determine how much force it experiences, we could calculate the magnetic field produced by wire number 1 over where wire number 2 is. So, in other words, we're going to use this formula to find the field which current number 1 is making. In other words, what's the value of those X's that we drew, right? How powerful is that magnetic field over where wire number 2 is? Now, the force on wire number 2, as we said, is given by this equation here. Okay, right, IL cross B. And I'm using the subscripts carefully here to indicate the force on wire number 2. The force on wire number 2, that would be this one, depends on its current and the magnetic field produced by the first wire, which we said could be found by using this equation. All right, so why don't we go ahead and plug that equation in down here and sort of rewrite the expression in a somewhat nicer way. And if we do that, we get this expression here. All right, which shows that the force depends on a variety of things. One of the things that the force depends on is current number 1. Okay, makes sense, right? The stronger that current is, the larger the value of the magnetic field it produces over where current number 2 is. The force also depends on current number 2. It also depends on the length of each of these wires. The way this is calculated, mostly it depends on the length of wire number 2, but our presumption here is that they're both very long and equally long. Okay, so it depends on the length. And then finally, it depends on the distance between the wires, which is r. Okay, fine. Now, what about the fact that wire number 2 also, since it is a current-carrying wire, produces a magnetic field? Doesn't it exert a force on wire number 1? And of course, the other question that should occur to us, does it exert a larger force or a smaller force or the same force, or would it maybe depend on which of these two currents was larger? All right, well, let's try and analyze that the same way that we analyzed the force that wire number 1 exerts on wire number 2. All right, step 1 in our reasoning is drawing the dots and X's. So wire number 2, everywhere to the left of it is making a field out of the page, as indicated by all of these red dots here, okay? Wire number 2 is also making a field that's into the page everywhere to the right of it, but that really doesn't matter because wire number 1 is, of course, off to its left. So the field that wire number 2 is making off to its left follows this function again. All right, fine. And the force on wire number 1 uses that same equation, F equals IL cross B. Okay, and then same idea, we're going to put 2 and 2 together, plug in this magnetic field formula, and we get this expression for the force that wire number 1 experiences due to wire number 2. Wait, hold on a minute here. Those are exactly the same. Yes, that's right. They are exactly the same, and that's actually the point. Remember action-reaction pairs from way, way, way earlier in the school year. Okay, well, those two wires, since they each produce a magnetic field, and each of those magnetic fields exerts a force on the other, should experience the exact same force. But since it's an action-reaction pair, they should experience that force in opposite directions. Oh, hey, speaking of directions, what is the direction of either of those forces? Well, this is where our first right-hand rule comes in. So all the dots and X's, remember we came up with those using the second right-hand rule that we had learned. Now we're going to use the first right-hand rule. Now, for the sake of clarity, I'm just going to go ahead and redraw the information from above. Okay, so wire number 1, number 2 are presented down below. And to begin with, I'm just going to think about the magnetic field that wire number 2 produces. Okay, so off to its left, it's making a field in the out of the page direction. Now, using your first right-hand rule, you should try to figure out right now what is the direction of the force on wire number 1, given that it's carrying a current up the page and that it's in a field which is out of the page, right? All these dots here. Okay, so it's carrying current up the page and it's in a field produced by the other wire, which is out of the page. Use your first right-hand rule, figure out the direction of the force on it. And my right hand, once again, has the answer, right? My palm is pointing up the page. Okay, that's the direction of the current. My fingers are curling, pointing in the direction of the magnetic field, and the force is to the right. Okay, so wire number 1 experiences a force to the right. Well, let's repeat that process now for the force on the red wire. Now, see if you can do the whole process on your own before you resume. The idea here would be draw the field that current number 1 produces. Then use the first right-hand rule to figure out the direction of the force on wire number 2. Okay? So we're using both right-hand rules here, right? Rule number 2 first, then rule number 1 to find the force. So you try it, then resume. Okay, so you can see the dots and X's that I have drawn, or at least I hope you can intuit their presence, right? So over where wire number 2 is, there are X's, right? The field is into the page, the field produced by wire number 1. And since the current is up the page, that's the direction my hand points, fingers curl into the page, and the force on wire number 2 is to the left. Okay, so wire number 1 experienced a force to the right. Wire number 2 experienced a force to the left. Well, look at that. That means those two wires are attracted towards one another. And so this actually is going to be a general conclusion that we can make about this type of situation. That is to say, where currents are going in the same direction. Currents in the same direction will always attract each other. Okay, so that's always going to be true. Any two wires which carry current parallel to each other are going to be attracted towards one another. Oh wait, what about if the currents go in opposite directions? What then? Well, I bet you have a guess. You're probably going to guess they repel, but let's go through and prove it using the same kind of reasoning that we just used for this one. Now, again, you should pause me, try it yourself, right? Do all the dots and X's, start to finish, before you resume the video and watch me doing it. If you can do it on your own, then you get it. If you can't do it on your own, then watch it until you feel like you do get it. So at this time, you should pause me. So wire number 1 is making that kind of a field. Right-hand rule is casting a vast shadow. Okay, well, current is down the page, field being into the page as my fingers are following. The force then is to the right on wire number 2. All right, now what about wire number 1? The red wire, wire number 2, makes that field. And the right-hand rule shows that this up the page current in the field going into the page experiences a force to the left. Okay, so altogether, the result is those two currents, which are in opposite directions, are experiencing a repulsive force. And so our guess was correct. Currents that go in opposite directions will, in fact, repel each other. Okay, so far what we've established in this video is that you can calculate the value of the force that the two wires exert on each other by putting together two equations, F equals ILB, and the equation for the magnetic field. And it kind of doesn't matter which way you want to think about it. Okay, you can think about one wire as experiencing the force and the other wire as producing the magnetic field that causes the force. Or I can reverse all of those subscripts right there. It really doesn't matter. Okay, either way, the final answer for the amount of force the two wires experience will be identical. The other thing that we've established is the direction of those forces is such that currents that are going in the same direction will always experience attractive forces, whereas currents in opposite directions will always experience a repulsive force. Now, for a variety of reasons, we will usually not actually do problems where I ask you to calculate the force on two very long wires. And part of the reason why is that the answer that we got previously is actually a little bit off. Because when you start getting near the ends of the wires, it starts to be incorrect, which is inconvenient. However, we can do a problem here on the force that a very long wire exerts on a loop of wire. And for that, we're going to have to break to the next video.